Hey everybody, welcome to my living room. Not exactly where I wanted to be teaching calculus today, but we will do what we can in these uncertain times. So today our goal is to go through the next 3 pages of notes. So we'll kind of review a little bit about average rate of change. We'll talk about what happens when the average rate of change itself is changing. And then we'll talk about exponential and logarithmic functions. So just as a reminder, the last time we talked about, well, kind of some mathy content was last week on Friday, when we said, we were talking about the average rate of change of a function. And we said the average rate of change, for a function f on an interval from a to b, which is a measure of inputs, is going to be given by this formula, f of b minus f of a over b minus a. And we know that formula, right? It's just the slope of the line that connects to those 2 points. So we kind of took a picture of this, saying we could have some sort of function doing whatever it wants in between here. But then for this point and this point on that function from A to B, we can go ahead and take a straight line and measure that slope. That slope is the average rate of change. So let's explore this a little bit further. As we do our example blocks in this video, I would highly recommend that you pause, at least take a minute to try it out on your own to see where it goes before watching the rest. I understand if you don't do it for every block, but I would recommend it if you can. So the idea for this example is talking about what does the average rate of change tell us about a function. So let's sketch a nonlinear function, which has an average rate of change of 1 on the interval from 0 to 2. Well, I'm going to need some axes, right? So we'll go ahead and try to draw some of those in. And I know that my function is going to be measured from 0 to 2. Great. That means I know the interval that we're exploring, right? It looks like this. So if I wanted to start looking at the formula for average rate of change, I would say f of b minus f of a over b minus a. And as a reminder, in this case, 0 is a and 2 is b. So we can get a little bit of work here. 2 minus 0, f of 2 minus f of 0. And as a reminder, I want this to be 1. So I could do something over, 2, which is going to be equal to 1. Well, common sense tells me that the difference between f of 2 and f of 0 better also be 2, because then 2 divided by 2 is 1, which is what we want. So as long as I can make that happen, really anything goes. So for example, what if I wanted to say that f of 0 is 1? That seems okay. And maybe f of 2 is going to therefore be 3. I never said this was to scale. So the slope of the line connecting those 2 points will definitely be 1. But I can kind of draw in whatever sort of function I want to do this. What if I have something that looks like this? Well, that will work. Or I could do something that is a little more rambunctious. That would also work, as long as we have that the slope of that line is equal to 1, which we do. We made sure that that happened when we plotted those 2 points. And I wish we could compare sketches at our table, but maybe you can already kind of see where this is going. What does the average rate of change tell you about the function? Not a whole lot. Mostly because we can kind of do whatever we want between those endpoints. And even still, we got to pick where we put those endpoints, right? I got to pick 1 and 3, but I could have picked 2 and 4, or 3 and 5, or -3 and -1. As long as I had it so that the top number, that difference right up here, was indeed equal to 2. So the takeaway here is that average rate of change will tell you how much we change in that interval and not much else. It doesn't tell us if our function is really highly fluctuating or if it's nice and smooth. Is it always increasing, or maybe it goes some increasing and then some decreasing? We can't necessarily tell with the average rate of change. So now we're going to talk about measuring changing change, right? So that average rate of change is not necessarily constant for a function the whole time. So we'll get back to this question, but let's see an example. So here I'm going to draw a function, and maybe it'll look something like this. And if I said, what's the average rate of change of this function? Well, it matters where I measure. If we measure closer to 0, maybe on this interval, the slope of that line is pretty steep. Hard to say what it is, right? I didn't give any numbers for this axis, but it's pretty steep. If I measure further away, it's much more shallow. So the average rate of change changes itself as we move through this function. And that's going to be pretty common. And I say often. Specifically, when we don't have a line, one of the things we talked about is that linear functions are great for modeling changes of variables that have constant rates of change. Well, if we don't, then that's every other type of function. So when is it not constant? When we don't have a line. Oops, there we go. When we don't have a line. And that's pretty often. So we want to be able to talk about this change as well, just like we talk about like increasing, decreasing. So that means we have some kind of average rate of change is changing itself. And how do we measure that? Well, let's take a look at our purple example before we get into those definitions. For this particular picture, we have something that has a pretty big average rate of change and then a smaller average rate of change. So it looks like my average rate of change is getting smaller. But if I would have drawn something, maybe that looks like this, it probably wouldn't be so hard to see that this is pretty shallow and it's pretty steep up here. That would be an increasing average rate of change. That is the distinguishing factor between these two definitions, concave up and concave down. So a function is concave up if its average rate of change is increasing. So that's that green one. So something that's concave up would be like x squared. Well, a function is concave down then if its average rate of change is decreasing. That would be like this purple one. You'll also see I say bent up and bent down. That will make a little more sense when I draw this little chart down here. So we'll get there. So maybe like negative x squared. Or that purple one kind of looks like a square root function. Possibly. And we're going to see lots of different examples of this, particularly when we get into exponentials here in a minute. However, one quick thing to notice is that concavity and increasing and decreasing have nothing to do with each other. So I have this little chart here. We're going to say that this row is going to be concave up. This row is going to be concave down. This column will be increasing. This column will be decreasing. So let's even just take our pictures here and try to understand, increasing or decreasing. So that purple one we decided was concave down, but it's still increasing. So let's go ahead and put it in the concave down increasing chart. Just a little sketch. And the green one, we decided was concave up, but it's also increasing. Something that looks like this. So how do we draw in kind of the decreasing versions? I'd recommend you take a second. See if your sketch matches mine. Here I have concave up and decreasing. I have something that looks like this. It's still kind of up like a cup, right? Which is a phrase that people use to remember concavity. And you can actually kind of tell that this is going to be concave up by looking at those average rates of change. But you might be saying, Kristen, it's getting flatter. But remember, this is a negative average rate of change here. So it's like negative like 5 maybe. And over here, maybe it's like -0.5. And that is actually getting bigger, right? It's getting less negative. So maybe not too surprising. The last part of this chart looks like this. And sketch those little average rates of change lines to kind of convince yourself that this is how this should go. We're going to be talking a lot about this, particularly when we get into exponentials, which is right now. So when we talked about linear functions, we said we were looking at functions that were having constant rates of change. Well, here we want to have a constant proportion of change. There's something really different there, which we will see in a second. So linear functions have a constant rate of change, which is exactly the slope. We're going to now go to something that has a constant proportion of change. That's called an exponential function. So an exponential function has one of these two forms. P is going to be our dependent variable, or P of t is the function. And I read this either as P0 or P naught, which I think is actually NAUGHT, but it's fine. They will sound the same. E is the natural number E, right? Like 2.7-ish or so. Yeah, 2.71, which we'll see here down here in a second. And you'll notice that R is a parameter. So R means something that I can change to bend my function. So both P naught, probably too big, let's shrink that a little bit. Both P naught and R are numbers that we change to change how the function looks, which we'll again see in a minute. T is our variable. We can tell because we see T right here. So there's a lot of letters in there, but we have two parameters, P naught and R, which will be set in the function. Think of them like how we have slope and y-intercept. That's kind of like this. And we have one variable, which is T. On the other side, we still have our two parameters, but they look a little different. P naught and A are how we're going to bend the function around. And our variable is still T, which we see in here. So we're going to talk a little bit more about them, but these functions are really common. Functions that are exponential often have written descriptions, like doubles every 10 minutes. If you've ever talked about like bacteria growth or like rabbit populations, things where it says, oh, the population doubles every 10 years or something like that. That's something that's going to be an exponential function. Or loses 15% of its area every year. Maybe something like, cutting down forests or something like that. Both of these have something to do with a multiplicative factor. What we mean by that is talking about doubles. That's like ×2, right? Or loses 15%. Well, what you're left with is 85%, right? So maybe times 0.85 every time, not growing by a certain amount, but changing by a multiplicative factor. That's the constant proportion, which we'll talk about. So here are some examples of exponential functions. Savings accounts, when they talk about compounding interest, annually, you'll have something that looks like this. So notice here that even though we've changed the letters, not a big deal, we still see some kind of like not function here. And then we have some sort of growth parameter there, 1 plus R. Beta decay as a function of time of some type of silver isotope, right? Here I again have my dependent variable with an independent variable. I used E, have some kind of growth parameter, and T is my variable again. And a forest being cut down a rate at 2.9% every year. Similar, we have some kind of multiplicative factor, an initial amount, and our variable. So we'll see those hallmarks a lot during our kind of time with exponential functions. One quick thing to note. If we want to use the function e to the x in RStudio, or R, we're going to call on a built-in function called exp. think of this like square root. If you try to run e caret x, it won't like it. So you can certainly try and kind of see what the error message that comes up, but we're going to use this built-in function for exponential. Think of this like square root, right? You know how we use like sqrt for square root or sin for sine? Same thing happens here with exponential. And we can see our make fun, something we saw a little bit on Wednesday, where we have an exponential function of x in terms of x, and we can evaluate it at 1. So this would be y equals e to the x, and what we're evaluating here is y maybe at 1, which would be e to the first, which is just e. So now that we kind of know what an exponential function is, we're going to actually try to plot some. So pause for switch to RStudio. Okay, welcome to RStudio. Here we're going to be talking about the block that we just talked about, which is trying to create a plot in RStudio that has y equals -2 e to the 0.5x and y equals 3 times 0.89 to the x. So we're going to go ahead and make a code block for this, and we'll just kind of do this together, right? In terms of plotting functions, I know we kind of left it a little bit hurriedly on Wednesday, so go ahead and watch along, code along if you want to. So what we'll do is the first thing is make a code block. So you'll see I have an R code block, so just go ahead and add it. As a quick reminder, I saw this a little bit on Wednesday. These 3 little dashes kind of open and close the block, so we do need to keep them around. So let's make 2 different functions. I'll maybe call them y1, which I'll do make fun. And I will go ahead and find my numbers here. -2 exp of 0.5 times x in terms of x, right? So what you'll notice is that's the first one I have in my notes. I keep looking down because my notes are down here. So that's the first function that we have. And what we can do here is make another one. Make fun. And it looked like I had 3 times 0.89 raised to the x in terms of x. So there are 2 differences here. I'll try to zoom in a little bit. So I have these 2 functions. I'm going to go ahead and run it, and hopefully it goes. It did for me. So here I have y1 and y2, so you can tell that it ran. Well, let's get a plot of this. So in that same block, or we could do a different block, that would be fine. What I want to do is plot fun. And I already have my function names, right? y1 of x in terms of x. Make sure that this runs. And we get something a little ridiculous, so we'll get back to that. Plot fun of y2 in terms of x. If I run that, maybe unsurprising, I get 2 different plots because I asked them to plot separately. It gave me one, and then it gave me the other. If I want these 2 together, we can do that. What we're going to do is add equals true. So that's a parameter that we're going to pass into the plot fun function that says, put the 2 plots together that be like you just built one, add this to the next one. And we have something that looks like this, which isn't great. So maybe I want to do a certain type of range, right? So we decided that xlim is how we're going to change our range. And maybe I only want to go from 0 to 3. Go ahead and run it. Oh, my bad. When we make our plot, we have to put the parameter up here because it puts that into the first plot that we make. Think of it like overlaying transparencies so that you can like say, okay, a plot made the structure of the plot on the first one, and then I'm going to overlay like a blank transparency of the second one. So hopefully this comes out looking a little better, and it does, right? We're like, but I don't see both. It's probably because we need to change our y-lim. Maybe I'll do -10 to 10. Go ahead and run that. And we see something here. We do have two plots and they look a little bit different, and it depends on kind of what those numbers are in terms of what the shape ends up being, which we'll explore a little bit more in general. So as a quick review of the code we just did, the first block actually made the functions. The second block actually kind of went and graphed the functions. We learned two things here. If we wanted to put two functions on the same plot, when we graph the second one, we're going to go add an add equals true parameter. And if we want to change the window, we have to do it on the first plot. So great, got a plot going. Pause for return to notes. All right, back to notes here. So we did just work on this particular block. We saw a nice way to get a plot where both of those functions are indeed on the same plot. And we definitely saw that the numbers that were there really affected how much those functions bend and what they look like. So let's explore that a little bit more. On the Moodle page, you will actually find a link to an online graphing calculator called Desmos. Now, Desmos is fantastic, and I think it's really useful for visualizing functions quickly, but it doesn't have like the data capabilities that this that RStudio has. So we don't use it all the time, but it's gonna be really helpful for us right now. So you'll find a link to a Desmos function, a workspace that has the two exponential value or functions that we looked at, both forms. These ones right here. They're going to use some different letters because Desmos wanted, simpler letters for our sliders. So I would highly recommend that you go around and start pulling those things. I'll kind of pull that up for us here in a second. Okay, so here's the Desmos workspace if you went and found it. And we have two different functions here. Here we have the one that has the E in it, AE to the RX, right? We still have that R, but I've used X instead of T because Desmos wants Y and X. And we see the one where we have B A to the X, or some kind of different like growth parameter that's not E. What's great about these is that you can pull them around and notice how the function changes as you change these parameters. So take a second and see what you notice about what happens, because weird things can happen if you, pull this way. What is going on in there? Kind of a thing. So take a second and try to see what you notice about this, and we'll kind of summarize the ideas in a second. All right, welcome back from Desmos, everyone. Hopefully you kind of got a good idea as to what these different parameters do in terms of changing how the function works. So you'll kind of notice I've color coded them a little bit here because we can kind of pair them in terms of their role in the exponential function. So the first one we'll talk about is capital A and capital B, those leading coefficients. Well, that determines the y-intercept. And I like to think of this as kind of the starting point, right? That's also why we see A sub or P sub naught, right? Because when X equals 0, in both of these cases, either you get capital A or capital B. That's what the y-intercept means here. So if we're thinking about where we start and how we're changing, we're probably talking about X equals 0 continuing onward, particularly when we talk about time. So that's going to be our y-intercept. And if you're not exactly if you didn't see that part, go ahead and try to leave this fixed and change one of the other parameters, either R or A, depending on your function. And you'll notice that the y-intercept doesn't change, right? It's kind of that little fixed point that the function bends around. So now we're going to talk about the other parameters. They also play the same role, but in different ways. They kind of determine if we have either growth or decay, depending on what the values are. And you probably notice this too. As you change maybe say R, you're either going to get something that looks maybe like this, or something that maybe looks like this. Right? That's growth. Oops, I made a mistake there. Sorry. There we go. That's growth. That's decay, right? So in terms of what we have for the factor, that's what's going to determine growth or decay. So if you have a negative coefficient, you might want to be careful and say, okay, is it actually growth or is it decay? Because that depends on the parameter, either R or A, whatever one you're using. So for growth and decay, we'll kind of make some rules here. You probably noticed this. If R is greater than 0, you have growth. If R is less than 0, you have decay. Now for A, it's a little bit different. If A is greater than 1, we have growth. If A is less than 1, we have decay. Now, just a quick reminder, when we determined these functions earlier, we kind of skated over these like range of possible values, right? For here, like in this one, R can be anything. But in this one, A can't be negative. If you tried a negative A, you probably noticed that there were some dots, because you can't always raise like a negative number to a power and get a really consistent function, right? Think if you wanted to do like -1. Well, -1 to the first is -1, but then squared is 1, and jumps back down to -1, then 1, and so on and so forth. But it gets really complicated, so we just don't allow for it, right? It doesn't necessarily make sense for things that like maybe X isn't, a nice whole number like 1 or 2 or 3. So that's where we get those values, and you definitely see that reflected in the graphs. So first parameter determines y-intercept, the R or A determines growth or decay. That's kind of our big ideas here. So how do we notice it from data? One of the things we really talk about in this class is being able to say, well, in various forms. Okay, so how do we notice this from data? Well, one of the things we talk about in this particular class is wanting to be able to notice a function in various forms, right? Talking about, well, what if I have a symbolic? What if I have a graph? What if I have a table? Things like that. And when we talked about linear functions, we could quickly recognize it from a table. Basically, you wanted to have a same added factor kind of going as you change X, Y changes by the same amount. So let's see what we can do here. Here I have this following data where if I'm looking at soybean production in millions of tons from 2000 to 2005, which is a little bit old for data, but we'll use what we can. Let's look to see if this is a linear function. If you think it's not, because it's in the exponential section, you're on the right track, but we'll see that it's not linear here in a second. What you'll notice is that here, the change looks like it's going to be about 9.3 in 1 year. But if we look later, we see that the change is going to be, looks like 11 point, oh, I'm going to have to do mental arithmetic, right? Live in front of people. All right, 11.7, I think is correct. And so we don't have that constant added change for a change in 1 year. So it's probably not going to be linear. So let's think about exponential. Well, if we're looking for a constant multiplied factor, we can try to figure out what we multiplied 161 by to get 170.3. And the way we do that is, well, think of the algebra. 161 times, well, I'll do a little star for times something, which I'll maybe call X, gave me 170.3. So if I want to solve for X, I just divide. And I did it ahead of time, and I get just about 1.058. So it looks like I multiplied this by 1.058 to get to the next one. And if you keep going down the list, you'll notice that that's the same every time, or approximately. You can try the rest out for yourself. Take 180.2 and divide it by 170.3, and so on and so forth. That's that constant proportion of change. Instead of adding it, we're multiplying by it. Just so we can get a look at that data, you'll see a plot points command here, where I have my Y values or my production values in the front and my years in the back. What you might notice is that I only took, the last digit, right? So you can think about the X values here as years since 2000. So 0 would be actually 2000, 1 would be 2001, same thing from there. And we see something that's really hard to tell if it's a line or not, right? Maybe you're kind of thinking, oh, I can tell if something's exponential, right? I can just graph it and they look totally different. Well, when you don't have a lot of data points and the factor is pretty small, you might not necessarily know, and that's okay. So how do we actually make this function? We look for that constant proportion of change. So linear functions are constant added factors, where exponential functions, I'll write it out, are constant multiplied factors. And it turns out that once we have this, it's actually not too hard to finish making the equation. So our next example block, and our last one for this set, is to find an exponential model for this data. Find the multiplicative factor. Great, we did that. We can do this one together. Times 1.058. It says, using the data from the table, write the equation for the exponential growth. Well, we actually have everything we need right there. 1.058 ends up being the constant multiplied factor to the t. And if we remember our discussion about how this ends up being kind of the initial amount, this is going to be 161. Let's do two mental checks here. First mental check. If I put in t equals 0, this whole thing goes to 1, right? Equals 1 is what I mean there. So if it equals 1, well, it should be whatever we actually get, 161 times 1. So you can kind of do a quick arithmetic check there. Second thing to think about is, why did I put that multiplied factor as the base for like little a, or whatever the letter we use for it? Well, it turns out that that's exactly what it's supposed to be. Think about this table. We decided that we start with 161 and then we multiply by 1.058 to get to the next step. And then to get from there, we took this number and multiplied it by the same factor. In some sense, what we've just done is take 161 and multiplied it by that twice. And then the next one would be 3 times, which is exactly what t is doing here, right? It says, okay, how many times should I multiply by 1.058? Is it 1 time? Is it 2 times? So we should do it squared. 3 times? That would be when t equals 3, and so on and so forth. So that's kind of the way that this happens. Once you actually have an initial data point and that constant multiplied factor, these come together very quickly, a lot like lines. So in terms of checking your answer in R, we will do that when we get back together on Monday. So a quick video summary, right? We talked a little bit about change, average rates of change, and how they themselves change with concavity. We talked about what an exponential and logarithmic function were, different types of forms of them, how to graph them, what their parameters do, and how to spot them from data. So we were planning on spending 2 days here anyway, so please bring your questions in on Monday if something's not necessarily clear. Otherwise, I'll see you then.